Okay, so here, well, welcome. And so what we're going to do is we're going to start today. This is the next video in hypothesis testing. And so this time we're going to start with the different methods for doing a hypothesis test. So this is another one of the steps, one of the 7 steps, but we're going to do it in 2 parts. I'm going to show you the traditional method of doing the hypothesis test and how to do the comparisons and how to do a left tail, right tail, and a 2-tail test for using the traditional method. And then what I'll do is in the next video show you the p-value method, and then in the following video we'll put it all together into the 7 steps. So that's why I decided we'll do it. It'll be easier to chunk this out that way. So this video will all be about the traditional method. So again, we're going to assume the null is true, and then we're going to use the sample data to test that assumption. And we'll see if there's evidence against that assumption or not enough evidence against that assumption. So let's use this idea. Let's use an example. So I'll use this example, and then I'll use the traditional method, and then I'll go through the different tests and different tail tests and things like that. And then next time I'll do the p-value method. So this is all going to be about the traditional method of doing a hypothesis test. So the traditional method involves 2 pieces. It involves a test statistic and a critical value. Okay? Well, I'm going to show you what the test statistic is and how do you get your critical value, and then how you compare the 2. And we're going to start with the mean. Later on we're going to talk about other parameters like p. But right now we're going to just stick with mu, the population parameter for the mean, the population mean. And then once we get to the other parameters, it'll be very similar, okay? So remember, we start with the null hypothesis. So that's going to be the same, and the alternative. And then what we're going to do is we're going to do our test to see whether we're going to reject the null or not. That's the test. So let's use this as an example here. It says that a certain computer component is known to have an average time of 520 hours between failures. A modification is made to the component that is supposed to extend the time between failures. To test that the modification is successful, a researcher samples 100 of the components and uses the data to test the hypotheses at a significance level of 0.05. Okay, now, the claim is that the modification works. Well, what does the modification do? The modification is supposed to increase the time between failures for these components. So, what does that mean? The average time, so the claim is that the average time, right, the mean time between failures has increased, right? So that means it's greater than what? Greater than before, right? The modified components, the time between failures is greater than the time between failures, the average time between failures for the old components, which we're told is 520. 520 hours. So how does this translate to? Well, the average time between failures, what's that going to be? That's going to be mu. And they're saying that this is greater than, greater than what? 520. So that's our mu naught. So now this is greater than, which means it's going to be the alternative hypothesis, right? So we're going to do mu is greater than 520 versus what? Mu is less than or equal to. Mu is less than or equal to 520. Now, in this case, the claim is the alternative hypothesis. Okay? So everything we've seen before. And now, what tail test is this? So, remember, the alternative hypothesis tells us the test. So this is greater than, so the arrow points to the right, right? So this is going to be a right tail test. Okay? So we're going to assume the null is true, and the test we're going to do is a right tail test. Okay? Now, what information did they tell us? They took a sample of 100 parts, 100 modified parts. So there you go. There's n is 100. And they give us the standard deviation. Hold on a second. Hold on a second. Hold on, I'm looking for the standard deviation. Okay, hold on. Let me see, the standard deviation. Well, let me see what the standard, hold on a second. Let me see if I can get the standard deviation, because they don't have it in this example. Let me pull it up. Okay, hold on, sorry. Okay, so let me see where it's at. Okay, so let's say, because I can't find it, but I'll just make it up. So let's say that the population standard deviation for this claim, let's see, is, let's say it's, let's say it's 23 hours. So let's say that's the population standard deviation. So we have the standard deviation, we have n, and we want to test this as a right-tailed test. Okay? What other information do we need? No, that's it. And let's say, oh, x bar. Let's say x bar for the modified units. Let me find out. Hold on. Let me find out what this is. Let's say the average x bar for these 100 parts, let's say the average is 533. So let's say that's the information that we have. So we'll go with this. So now let's say this is our sample data. These are our hypotheses that we're going to look at. This is the claim, and we're going to assume. So remember here, we're going to assume, let's assume mu is equal to 520 hours. So it did not increase. Okay? We're going to assume that it stayed the same. So here's how the traditional method works. Our test statistic for the traditional method is going to be based on the sample. Okay? The test statistic in this case is going to be a z-score. And what I'm going to call z star. And z star is going to be our test statistic based on the sample data. And what we're going to basically do is use the sample data, and we're going to convert this x bar value, the sample mean, into a z-score. So we're going to use the z-score method, or the z-score formula. So it's going to be x bar minus the mean divided by the standard deviation of x bar, which is sigma over the square root of n. Now, at this point, what we're assuming is that we know sigma. So realize that sigma is known. Okay, so everything that we're doing for right now is under the assumption that sigma is known. Okay? Now, this is our test statistic, or z star, and it's just a z-score. Now, in order to do this, we have to know the distribution of x bar. So again, we have to know that the distribution of x bar is normally distributed, else we can't calculate a z-star that means anything, right? Remember, bell-shaped and symmetric. Okay? So we have to make sure that we have the correct distribution. So is x bar normal? And the answer is yes. Why? Because n is bigger than or equal to 230, right? So the central limit theorem tells us it's normal. Now, it's normal with what mean and what standard deviation? Well, it's the mean under the null. So it's going to be 520. And the standard deviation is going to be 23 divided by the square root of 100. Okay? This is what we're going to use in this calculation, because our calculation is going to be x bar minus mu naught divided by the standard deviation of x bar, which is sigma divided by the square root n. Okay, so now if we calculate, then now all we have to do is plug and chug, right? We know x bar, that's 533. Mu is 520 under the null. And then sigma divided by the square root of n is 23 divided by the square root of 100. So now, what do we get when we calculate that? Let's find out. So 533 minus 520. So we get 5.65. So 5.65. So that's our test statistic. Okay. Now, the second piece that we need is our critical value. Okay, so now let me hold off for a second. I want you to write this down. I'm going to erase this, and so keep this in mind. So the main thing is we got the critical value, or excuse me, we got the test statistic, Z star, from the sample data. That's what the sample data gives us. It gives us our test statistic, okay, which is basically our sample mean, but we convert it into a Z score, okay? Now, let me write that here. So our Z star we found out is 5.65. Now the other piece that we need is our Z critical value, our Z alpha. Or some textbooks or some people will call it Z sub C. Okay? Now, how do we get our critical value? Well, that comes from the distribution, and that comes from alpha, our significance level. So again, based on our significance level alpha, which is, again, the probability of making a type 1 error, this is where the test comes in. Since we know that the distribution of z-scores is normal, and that's what we're using as our test statistic is z star, then what we need to find is the critical value. And the critical value is based on the alternative hypothesis. So we're doing a right-tailed test. So our critical value is going to be over in the right tail. And we're going to call this z sub alpha. And the reason why we're going to call it z sub alpha is because, remember, back from confidence intervals, what is alpha? Alpha is the area in the tails. But in this case, it's only a one-tailed test. So alpha is going to be the area in the right tail. So for this test, alpha is the area in the right tail. So our critical value is the value that cuts off the top area that's alpha. Does that make sense? I hope that makes sense. So this is determined by alpha. So our critical value is determined by alpha and whichever tail we're using, which in this case is right tail. So this is what we need to use. Now, so how do we get our critical value? Well, since we know that the z-scores are normally distributed, right, we can use what function on our calculator? We can use inverse norm. Inverse norm will give us a z-score, right, or an x value, as long as we know it's normally distributed. So, and since we know all z-scores are on the standard normal distribution, we know the distribution's normal with a mean of 0 and a standard deviation of 1. So now all we have to do is put in the correct information. So inverse norm, let's do it this way. And so the first argument that we put in the calculator is the area. But what area? Remember, it's area to the left. Well, if we know the area to the right is alpha, and let's say alpha in this case is 0.05, right? If alpha is 0.05, and by the way, 0.05 is the most common significance level that you'll find. It doesn't have to be 0.05, but it is very common to use 0.05. So here, the 0.05 alpha, so we know the area to the right is 0.05, right? So then, what's the area to the left then? The area to the left is 0.95, right? The complement rule. And so now, we need to put the area to the left here. So we're going to put in 0.95 here, followed by 0, followed by 1, comma 1. And so what is the z-score in this case? The critical value? The z, oh, not z alpha divided by 2, it's z alpha, sorry. Z alpha. So in this case, z alpha is going to be equal to 1.645. Okay, so go and put it in your calculator. And again, you could also find this using the table, right? Because you could just look up 0.095, or excuse me, 0.95 on the table, and you can get the same z-score, 1.645. So again, you could use the calculator or the z-table. But the main thing is you've got your critical value. So now we got the critical value, and we've got our test statistic. Now what? Now this is where the test comes in, the alternative hypothesis. Because what we call the right tail, the area to the left of our critical value, or excuse me, the right of our critical value in this case, let me see if we got another color here. Okay, I'll just have to use this. Oh, hold on. Maybe this one. Nope. Okay. So this area here, this area to the right, this area to the right of our critical value is called the rejection region or the critical region. I typically use rejection region. So this rejection region, why do we call it the rejection region? Very simple. The rule, the general rule for the traditional method. So write this down. The general rule for applying the traditional method is this. If your test statistic, whatever your test statistic is, if that value falls within the rejection region, then we reject the null. So again, if your test statistic falls within the rejection region, we reject the null. Now, what that looks like for each test is a little different for the traditional method. Because in this case here, when will our test statistic fall within the rejection region? Well, if our z star is greater than or equal to z alpha. If our critical value falls within the rejection region, in this case, if our test statistic z star is greater than or equal to z alpha, then we reject the null. Okay? So now in this case here, that's the result. Based on these hypotheses, and based on the sample data that we got, we're going to reject if our test statistic is greater than or equal to our critical value. Now our critical value is 1.645. Is our test statistic bigger than or equal to our critical value? Yes. Huge, right? 5.65 is definitely bigger than 1.64. So does it fall within our rejection region? Yes. Are we going to reject the null hypothesis? Yes. What does that mean for our claim? If we reject this, okay, then that means that there is significant evidence or strong evidence or sufficient evidence to support the alternative hypothesis, which is the claim. Okay? So the traditional method is a two-part thing. So the traditional method starts with you have to find your test statistic using the z-score formula, and then use the calculator or use the table to find the critical value, and then use the alternative hypothesis to find out when you're going to reject. And you're always going to reject if your test statistic falls within the rejection region. That's the traditional method. Okay? So now, let's talk about the different tail tests now. So this is the traditional method that we'd go through. Okay? So now in general, let's just talk about the different tests, the different tails. Okay? So we have the right tail, the left tail test, and then we have the two-tail test. Let me do this. Yeah, let me do it this way. So I'm going to start here. You probably won't be able to see it. I'll do right tail, and then I'll do left tail, and then I'll do the two-tail. So the right tail is exactly what we just did. So with the right tail test, this is what we have. So a right tail test, our rejection region will be marked off by the right tail critical value, which is Z alpha. And remember, alpha represents the area in the right tail now, because it's a right tail test. And so the rejection region is this region right here. And so we will reject if our test statistic falls within the rejection region. And in this case, it's going to be if Z star is greater than or equal to Z alpha. Okay? And again, this is the rejection region. Okay. That's the right tail test. The left tail test, if you realized, but now, that it's going to be the other way. So here's our curve. And a left tail test means that our critical value is going to be on the left tail. So this is going to be negative Z alpha. Or in other words, we could also say Z1 minus alpha, since again, alpha in this case is the area in the tail. It's a one-tailed test. Alpha is always the area in the tails, or the tail. Okay? So in this case here, alpha is the area in the left tail. So we can call this critical value 1 minus alpha because typically the subscript always represents the area to the right. That's just by construction. Or we can just do negative Z alpha. So the negative value of Z alpha. Okay? In either case, you get the same answer. Okay? But it's the critical value. The critical value is the cutoff that separates the bottom alpha from the rest of the graph. Now, in this case here, how are we going to find our critical value? Again, we're going to use inverse norm. But this time, what's the area to the left? Right? It's always the area to the left when you use inverse norm. What's the area to the left? In this time, it's alpha. So we're going to put alpha in here, and then followed by 0, 1. Okay? So that's how you would get your critical value. Or you could use the table. Again, you could use the table and look up the area to the left on the table to get your critical value. Okay? Now, in this test, this is the critical region. So it's going to be the left tail. So in this case, this is the rejection region that we want to look at, that we want to focus on. So in this case, when are we going to reject? Again, the main guiding rule is that we're always going to reject the null if the test statistic falls within the rejection region. So for a left-tailed test, what does that look like? Well, it's going to be if z star is less than or equal to z1 minus alpha, or the negative z alpha, okay? So it's, again, if z star is less than or equal to our critical value, okay? So notice how the right-tailed test, it's greater than or equal to. Left-tailed test, we reject if our z star or critical is less than or equal to our critical value. So now what about a two-tailed test? Well, the two-tailed test, we have now two tails to deal with. So in other words, we have two critical values, or critical regions and critical values. Okay, so we have two rejection regions. So now, well, what's alpha this time? Alpha is the area in the tails, but this time we have two tails. And since we're dealing with a z distribution, it's bell-shaped and symmetric. Half of alpha goes here, half of alpha goes here. So it's just like confidence intervals. So now we've got two critical values. We've got z alpha divided by 2, and we've got negative z alpha divided by 2. Okay? Or we could put z1 minus alpha divided by 2, same thing. So now we've got two rejection regions. So with a two-tailed test, we're going to reject the null if our test statistic falls inside this rejection region, or if it falls within this rejection region. So in other words, we're going to reject if our test statistic is too small or if it's too big. Okay? So now, what's the rule? The rule is still the same. We're going to reject if our test statistic falls within the rejection region. It's just that we have two rejection regions that we have to check. In other words, and for this test, what we're going to do is we're going to reject if the absolute value of our critical or test statistic, if the absolute value of our test statistic is bigger than or equal to the positive z alpha over 2. In other words, if our test statistic falls within this rejection region and we make it positive, it will flip automatically over to this rejection region. So if we take the absolute value of our test statistic and compare it with the positive value, we'll basically take care of both possibilities. Okay? So that's it. That's the traditional method. So the traditional method is we calculate our test statistic. That's based on the data, and we use our z-score formula to transform the sample mean into our z-score z-star. Okay, and that's going to be our test statistic. Then we're going to figure out what our critical value is based on the alternative hypothesis. So it's going to be one of these three situations. And so we're going to figure out the critical value. Now, the critical value here, to find our z alpha divided by 2, again, is the same thing. What we're going to do is we're going to take the area to the left of this value. So the area to the left is going to be the middle area, right? And the middle area is always going to be, remember, the confidence level is 1 minus alpha, just like alpha is 1 minus the confidence level. Okay? So in this case, we're using significance level. The middle area is going to be what's left over from the two tails. So whatever alpha is, the middle is going to be 1 minus that. So now, well, now that we know the middle and we know what half alpha is, we can figure out the area to the left, put in the area to the left, the percentile, followed by 0, 1, and you'll get the critical value. So again, inverse norm will give it to you every time. Just make sure you know what area you're putting into the calculator, okay? So once you have your critical value based on the test, which tail test you're doing, then you just see, does my critical value, or excuse me, does my test statistic fall within the rejection region? And so it's either going to be this, or this, or this, okay? And that is how you do the traditional method. And so I'll leave it at that. And so next time, the next video, we're going to go and do the same thing. We're going to use the same example, and we're going to do the p-value method, and then we'll go from there. Okay, thanks.